Alright, let's jump right into this explainer and discover exactly how manipulating chemical recipes and processing transformed your basic, everyday metals into the literal building blocks of our modern world. When you stop and look around, almost everything structurally significant is made of metal, right? But here's the thing, it's rarely in its pure form. Instead, we heavily rely on alloys. These are masterful, intentional combinations of elements designed to achieve very specific characteristics. So today, we are exploring the vast universe of these materials, looking at how their microscopic structures dictate everything from how a massive suspension bridge holds up to how a tiny artificial joint functions perfectly inside the human body.
You know, to really wrap your head around metallurgy, it actually helps to think of it a lot like cooking. The basic chemical elements, well, those are your ingredients. And the processing steps, that's your preparation and your oven times. Take a humble aluminum beverage can, for example. It starts its life as a simple, flat sheet of an aluminum alloy. But then, through a highly controlled sequence of production operations, we're talking drawing, dome forming, trimming, neck forming, it gets totally transformed into a lightweight, pressure-holding vessel. It's wild. A simple change in that initial alloy recipe, or even just a slight shift in the fabrication process, and you alter the final product's properties entirely.
So we're going to use this taxonomic tree as our roadmap today. We'll quickly cover the metal alloy universe, then steels, stainless steels, cast irons, and finally we'll wrap up with non-ferrous alloys.
Okay, Section 1. The metal alloy universe. Ferrous versus non-ferrous.
Let's start with the absolute biggest, most fundamental split in our family tree. Ferrous alloys form the absolute backbone of engineering construction materials. I mean, they completely dominate the industry. Basically, any metal where iron is the prime constituent falls right into this category. Whether it's the massive steel beams holding up a skyscraper or the engine block inside your car, ferrous alloys are fundamentally shaping our physical infrastructure. In fact, they're produced in far larger quantities than any other metal type on Earth.
So you might be wondering, why do ferrous alloys rule the engineering world so completely? Well, they're so widely used because iron-containing compounds are just incredibly abundant in the Earth's crust. And that makes extraction and refining extremely economical. They're cheap. On top of being incredibly cost-effective, they are highly versatile. Just by tweaking the chemical composition, you can achieve a massive range of physical and mechanical properties. But as with everything, there is a catch. The primary disadvantage of many ferrous alloys is their high susceptibility to corrosion. Basically, we are constantly having to battle their main weakness, rust.
Moving on to Section 2, steels, the carbon connection. Now, as we move down the ferrous branch, we hit steels, where the carbon ingredient literally acts as the master dial for the material's properties. It's fascinating. Notice how low-carbon steels, which have less than 0.25% of carbon, trade extreme strength for just absolutely outstanding ductility and toughness. Take plain low-carbon steels like the 1010 or A36. Because they're relatively soft, they have this incredible capacity to be bent, formed, and welded without breaking. This makes them absolutely perfect for stamping out automobile body panels, laying pipelines, or building those massive structural I-beams we use in bridges. Plus, as a bonus, they happen to be the least expensive of all steels to produce.
But here's where it gets fun. As we crank up that carbon recipe, the entire character of the metal shifts. For medium carbon steels, which range up to about 0.6% carbon, the material becomes much stronger. This is perfect for high-stress applications like heavy railway wheels, gears, and crankshafts. Now, push that carbon even higher, between 0.6 and 1.4%, and you get high-carbon steels. These are the hardest, strongest, and most wear-resistant carbon steels out there. They are exactly what you want for sharp cutting tools, heavy-duty dies, knives, and hacksaw blades. But remember our cooking analogy? This extreme hardness comes at a direct cost. You completely sacrifice that previous ductility we talked about. High-carbon steels are by far the least ductile of the whole carbon family.
Section 3. Stainless steels, resisting elements.
So, remember that pesky corrosion problem we mentioned earlier? Well, let's explore a very specific branch of steel designed to solve exactly that. The absolute crucial point here is that adding at least 11% chromium to the mix is what gives stainless steel its legendary resistance to the elements. This chromium essentially acts as an invisible shield, preventing the underlying iron from ever reacting with oxygen and rusting. It's such a simple elemental addition, but it completely revolutionizes where and how we can use steel, especially out in the ambient atmosphere or in really severe chemical environments. And this is a brilliant example of how just tweaking the recipe a tiny bit further gives us entirely different classes of stainless steel with wildly different applications. We've got the Martensitic class, which you can heat treat for extreme hardness, making it ideal for things like surgical tools and premium cutlery. Then there's the Ferritic class, which you'll often see used for automotive exhaust components. And finally, the Austenitic class. Now, these are heavily alloyed with nickel as well as chromium. They're actually non-magnetic, and they are the most corrosion-resistant of all. Because of this extreme resistance, specific austenitic steels are used to create temporary orthopedic devices. We're talking plates and screws used to stabilize fractured bones, safely sitting right inside the human body.
All right, Section 4, Cast Irons, Microstructure Matters.
Okay, let's jump over to the next major branch of the ferrous family tree. And right away, we hit a fascinating paradox. Think about it. If we literally just learned that pushing carbon content higher makes steel incredibly hard and brittle, why on earth do we push the carbon content even higher, typically between 3.0 and 4.5%, to make cast iron? Wouldn't that just make it utterly, uselessly fragile? Well, the secret is fluidity. That extra carbon dramatically lowers the melting temperature of the alloy, down to somewhere between 1150 and 1300 degrees Celsius, which is actually considerably lower than steel. This creates a highly fluid liquid metal that is just incredibly easy to melt and pour. Because it's so fluid and because it shrinks very little when it finally cools, cast iron is absolutely perfect for pouring into complex, highly intricate molds. It allows us to create heavy equipment bases or complicated engine blocks that would be nearly impossible or prohibitively expensive to forge or machine out of a solid block of steel.
But here's the catch. What actually happens to all that excess carbon when the liquid metal solidifies? Well, when we look at the true equilibrium phase diagram, we see that in these high-carbon alloys, the carbon literally separates out. Instead of remaining locked within the iron matrix as a carbide, it precipitates out as pure graphite. And here is where it gets truly amazing for engineers. The actual physical shape of this graphite at the microscopic level changes absolutely everything about how the metal behaves in the real world. Just look at the microscopic structure of gray iron. The graphite forms into these sharp, cornflake-like shapes. Because these flakes have pointed tips, they act as microscopic stress concentrators. If you pull on gray iron, it's actually quite weak and brittle, because it essentially just fractures right along these sharp flakes. But check this out. By simply adding a tiny pinch of magnesium or cerium to the liquid right before casting, we force that graphite to form into rounded spheres, or nodules. We call this ductile iron. Because the graphite is perfectly round, there are no sharp stress points, which gives this cast iron high strength and ductility that actually approaches that of steel. It's brilliant.
And the control we have over microstructure doesn't even stop there. By very carefully balancing the silicon, magnesium, and other additives, modern metallurgists have developed something called compacted graphite iron, or CGI. The graphite here takes on a really unique worm-like shape. It's sort of an intermediate form, sitting between the flakes and the spheres. This specific vermicular microstructure provides amazing thermal conductivity and resistance to thermal shock. It's the absolute ideal material choice when you need something to handle rapid, extreme temperature changes without fracturing, which, as it turns out, is exactly why it's heavily used for the brake discs on high-speed trains.
Section 5, Non-Ferrous Alloys, Beyond Iron.
For our final section today, we're actually leaving the ferrous tree entirely to briefly explore the non-ferrous universe. Look, iron is great, but it's relatively heavy, it doesn't conduct electricity exceptionally well, and as we know, it rusts. So sometimes we just need a completely different base ingredient. Let's look at copper alloys, for instance, which are famous for their corrosion resistance and formability. Within this group, we can compare brasses against bronzes. Brasses use zinc as their primary alloying element. This creates a softer, highly ductile metal that is easily cold-worked, perfect for forming intricate musical instruments or stamping out cartridge casings. Bronzes, on the other hand, use elements like tin, aluminum, or silicon. This recipe yields a much stronger alloy with an even higher degree of corrosion resistance, specifically designed to survive and maintain its strength in much tougher, highly corrosive environments.
And hey, if you're sitting there thinking non-ferrous metals just can't compete with steel on raw strength, consider this number for a second: 1,400 megapascals. By alloying copper with just a small amount of beryllium and then applying a highly specialized precipitation-hardening heat treatment, we can achieve astonishing tensile strengths up to 1,400 MPa. These beryllium coppers possess this remarkable combination of excellent electrical properties, corrosion resistance, and extreme strength.
It totally showcases the incredible limits of non-ferrous engineering when your chemical recipe and your heat treatment are perfectly in sync.
So as we wrap up this explainer, I really want to leave you with a foundational thought directly from our source material. A materials problem is really one of selecting the material that has the right combination of characteristics. Whether it's adding a dash of chromium to fight off rust, utilizing a pinch of magnesium to force graphite into tiny spheres, or hardening beryllium copper for extreme tension, metallurgy is the ultimate exercise in intentional design. So the next time you're engineering a simple, recyclable aluminum can, or maybe even a life-saving surgical implant, what microscopic recipe will you choose to shape the world tomorrow? Keep questioning the materials around you, and thanks so much for joining me on this explainer.